Welcome back, everyone. So we have the pleasure now to hear the talk of Konstantin Vodopyanov, frequency comb spectroscopy from 1 terahertz to 1 petahertz.
Maybe we should chill wait for maybe a couple of minutes.
We have to keep the scheduled time.
Ah, okay. Let's check this. All right. Thank you for the introduction. So my name is Konstantin Vodopyanov. I'm at Creole. This is the College of Optics and Photonics, one of the major optical laser centers in the United States. And we are at the University of Central Florida, not far from Disneyland and not far from Cape Canaveral. There is a little bit of the background. Sorry? Yeah, okay. Perfect. All right. So I will talk today about frequency comb spectroscopy, and don't worry, I'll explain what it is for someone who doesn't know. So basically, I would like to start with a question. So how much time you need to take this spectrum, which is in the so-called mid-IR spectral signature region, where the molecules have their strongest resonances, and this range is between 3 and 12 microns. My question is, how much time will it take to scan this range with a resolution of, let's say, 1,000th of a wave number, which means high resolution, to resolve the Doppler line width in this range, which spans more than 2,000 wave numbers. I think with the traditional tuning laser, it'll probably take forever. At least it'll take many, many hours. So I would like to persuade you that actually with a dual comb spectroscopy, which I'll explain what it is in a second, you can do it in 12 seconds, actually. Take this spectrum with a superior resolution. So what is the essence of dual comb spectroscopy? First of all, about dual combs, few seconds about dual combs. So these guys got the Nobel Prize. Theodore Hensch and John Hall got the Nobel Prize in 2005 for frequency combs, which is basically an infinite sequence of ultra-short pulses, and they can be carrier offset stabilized, as shown here. So basically, every next pulse has the same alignment of the carrier and the waveform, or they can be not, but still it is a frequency comb. So if they are carrier offset stabilized, then this corresponds basically to a sequence in the frequency domain, a sequence of delta functions in frequency, which can be 1 octave or more, and which can contain up to 1 million comb modes. And so here is the example where they're on this side, where they used an astronomy, because this is an ideal ruler, and of course for many, many other applications. An ideal absolute ruler with delta functions, which are reference to rubidium clock or GPS or whatever clock you have now, the best in the world. Okay, so now, what is dual comb spectroscopy? In 2004, Fritz Keilmann invented actually that technique and demonstrated that experimentally, because he said, we all know about Fourier transform spectrometer and Michelson interferometer. So he said, instead of the second arm in the Michelson interferometer, which is the moving arm, you just take another laser, another femtosecond laser, which has more or less the same spectrum as the first laser. And then, so you take a mode-locked laser, which is number 1, and number 2, let's say with 100 megahertz repetition frequency. And you take another laser with this tiny offset, fractional 10⁻⁶, let's say with an offset of 100 hertz with respect to the first laser, and then you coherently combine them. And so then you'll have automatically the sliding delay without any moving parts. And I'd like to persuade you that this technique allows to improve traditional Fourier transform spectroscopy by a million times in all senses, in the speed, the resolution, etc. So that's another way. So this is basically the same. So the two laser pulses with a small offset of repetition frequency, one pulse slides through the other pulse periodically. And so, and then just based on the Wiener-Hintschen theorem that the Fourier transform of the cross correlation, this is the cross correlation which you see on the bottom in blue, is the power Fourier spectrum. So, however, there's no moving parts, but you need to have the second laser which is perfectly phase locked to the first one. And this is the hardest part because you need a lot of stabilizing electronics to do that. And once you do that, actually you can get a lot of advantages. For those who prefer frequency domain picture as opposed to time domain picture, I can also explain that in the following way. So imagine that you have a frequency comb, and let's compare that to a simple comb for dogs. So you have a million comb teeth, and then you want to look at the molecular absorption, for instance. How would you know where the molecule, which one of these million combs is absorbed? How would you know? So the trick is that the dual comb is that you take another comb with a small offset of the comb tooth spacing. And then when you combine them coherently, basically you will see the position of your comb tooth would be encoded in the beat frequency. And you can see here that beat frequency increases here from left to right. So so the optical frequency will be encoded by the radio frequency with a known coefficient. This coefficient is usually on the order of 1 million, which is very well known. So in frequency comb community, everything is well known because all these combs are linked to the atomic clock. And so they're no longer nanometers or angstroms. People use everything in hertz. And so now the people who got Nobel Prize in 2005, they did it in the visible range, titanium sapphire, visible near-infrared range. The most interesting for molecular detection, for instance, for microbiology and other fields, is mid-infrared range, because it contains all the molecular signatures, all the resonances are there. So how to get into the mid-infrared using near-infrared combs? So one technique which we invented when I was at Stanford is the frequency divider by 2. So the idea is that you make an OPO, optical parametric oscillator, sync pumped OPO, on the femtosecond pulse. It can be titanium sapphire or erbium fiber. And then you drive, basically one photon is split into, decays into 2 photons, and then you drive the signal and the other photons towards the generacy. And this is something which historically people did not like to do, because when they come to the generacy, they are not aligned in phases, and then you have a mess. So, and we managed to tame that, and once you do that, using some piezo control of the fine piezo control, then you can see that basically the pump frequency comb is converted into the very broad subharmonic frequency comb, which inherits all the coherence properties of your pump. So your subharmonic comb is as good as the pump, but it can be broader, because nothing prevents you to conserve the photon energy. You create one photon here and one photon here, and still the sum of the photons is equal to the pump. So that's one technique. In time domain, you just produce a subharmonic, and then this becomes a very useful comb, which we used. This is our Nature Photonics paper. We used that in 2017 to demonstrate massively parallel detection of molecules in a mixture at trace amount from 10 to minus 6 to 10 to minus 9. So basically, we built the 2 absolutely identical subharmonic OPO by 2 identical thulium fiber combs at 2 microns. which were, everything was locked to the frequency counters were locked to a rubidium clock. And so its precision was like 10 to minus 10 in terms of the absolute time frame. And then, so the two beams can be combined before the gas cell, which is equivalent to a symmetric scheme in the Fourier transform, or before, which was a symmetric scheme. But anyway, you just use a single medium thread detector and take Fourier transform, and then you get this wonderful molecular spectra simultaneously. So looking up is experimental peaks, looking down are peaks from the database, from the HYTRAN simulated peaks from the HYTRAN database, and you can see that there is a very good correspondence of our data with the HYTRAN. So, and then we're very proud that we started even providing the international molecular databases like HYTRAN with the data which were never measured before. Like this is the CS2 molecule, which is molecule number 53 in the HYTRAN molecular database. And just in a single measurement, we generated this close to 1,000 lines, which our theory partners all deciphered them and made the so-called line list. So basically they, in the frame of quantum mechanics, they explain all these lines, rotation, vibration transitions, including isotopes of carbon and of sulfur, and including the hot bands. So basically they will tell us what these bands are. So this is just proves the precision of this technique. And so we did that with actually we used that technique with many different pump lasers, starting from Urban at 1550 and ending with chromium zinc sulfide lasers. This is a mid-thread femtosecond laser close to 0.4 microns, and with different crystals, including lithium niobate, gallium phosphide, gallium arsenide, and even zinc selenide. So that works. And our second approach is called optical rectification, which allows you to go even further into the mid-infrared. Because the first technique, with the first technique, you get kind of 2 lambda, roughly speaking, of your pump laser. So if you have 2 micron laser, you get something around 4 microns, plus minus, let's say 3 to 6, but not much further. So optical rectification is a very nice technique, which was actually invented by Austin. I think the first paper which I found in optical rectification, 1984. And this is just based on the simple fact, and this technique was widely used by, and is, by terahertz people. So when you send a ultra-fast near-infrared pulse through electro-optic crystal, or the same as nonlinear crystal, you create nonlinear polarization, and this polarization gives rise to the terahertz fields, or long-wave mid-IR fields. So this is the picture. So basically, you generate a single multi-cycle pulse. You generate a single cycle long-wave pulse, and that's interesting that this pulse does not have carrier envelope offset. So it's always independent. So basically, the non-zero carrier envelope offset of the short pulse drops out, and you always generate like a single pulse, which looks always like that. In the frequency domain, this technique is equivalent to self-frequency, nonlinear self-frequency mixing, because you usually use a very short pulse with a very broad spectrum, close maybe to an octave. And so you mix, inside the nonlinear crystal, the mixing happens between the blue component, the red component, and so you generate the difference in the long wave part of the spectrum, studying from terahertz and all the way to maybe 3 micron, depending on the duration of the pulse. And so then at some point, we found that there exists this absolutely wonderful new laser, which is an analog of titanium sapphire, but works in the mid-infrared at 2.4 microns, which is called chromium 2+ zinc sulfide laser. It is very similar to titanium sapphire in all the senses. So its relative bandwidth is like 30% the same as titanium sapphire. It has the same lifetime, has very high gain, and is ideal for Kerr-Lens mod locking. So this laser can be easily mod locked without using any nonlinear set of absorbers, and can produce, in ideal case, the spectrum as broad as this one, from below 2 microns all the way almost to 3 microns, and producing few cycle pulses, maybe from all the way down to 16 femtoseconds, 2 cycles. And it can also work at different repetition rates from 80 megahertz and to build above 1 gigahertz. So wonderful laser, we liked very much, and we used, and it perfectly suits for optical rectification. We use these 2 nonlinear crystals, ZGP and gallium selenide, and just by a single pass through a crystal, we can produce this ultra-broad spectrum exceeding an octave. So in this case, it goes from 6.7 to maybe 15 microns. Gallium selenide allows you to go to longer waves and even to terahertz. In this case, the span of the comb is 9 to 22 microns. I should say that the laser, it preserves the frequency, the coherence of the frequency comb, because if you have a very nice laser, if you have a very nice pair, which was made for us by IPG Photonics, a nice pair of dual comb lasers, then it will be preserved in the down-converted comb, because each of these spectra consists of, let's say, 500,000 comb lines. Basically, these are, and you will see that in my further slides. So this is wonderful, and so based on that, as I said, we now have a pair of these lasers which are phase-locked, which are nicely phase-locked to each other, which requires some electronics and a lot of feedback loops. However, when it is done, then the job is easy, because you just down-convert both of these lasers in basically 2 identical schemes, down-convert them in ZGP, in this case, ZGP crystal, and then you combine them, send through the gas cell, use a single detector, take Fourier transform, and then you restore the whole spectrum. It's shown here. It's about an octave, from 6 to almost 12 microns. When you spectrally resolve the spectrum, you can see that this frequency comb consists of these comb teeth, extra narrow, with a finesse of more than 2,500. And what is wonderful about dual frequency comb technique is you can do the measurement very fast. Of course, the signal to noise is improved with averaging. So this spectrum was taken for only a few seconds, and in fact, we published a paper in Optics Letters which says long-wave red dual comb spectroscopy with 240, like 250,000 spectral data points at a video rate. So in this case, we were able to obtain the spectrum at a video rate of 10 hertz. So this is really the power of the dual comb technique. So this spectrum compares, again, experimental on the top with high-tran at the bottom, and you can see all these tiny features of N2O molecules reproduced here on this slide. And then we realized that actually you cannot go there. There are many interesting things with molecules that happen at longer waves, because you can buy, for instance, an MCT detector which cuts off at 12 microns, and then if you want to go further, you need to buy another detector which goes to 16 microns, and if you want to go further into the terahertz, you want to buy even much more expensive detector which needs liquid helium, which is about bucket size. And so then we paid attention to another technique, which is called electro-optic sampling. Again, this was invented in the same paper by Austin and co-authors in 1984, so the essence of this is that instead of using, imagine that you want to detect a long wave mid-infrared field, which can be 10 microns, 20 microns. You send a very short near-infrared pulse, and you coherently combine them in an electro-optic crystal, the same as nonlinear crystal. And so the near-infrared pulse, this one, its duration needs to be shorter than the cycle of the mid-infrared pulse. So basically, it will see, for this pulse, this will be like a DC field, and this will change the pulsation state of the near-infrared pulse, which then, so the presence of the near-infrared field simply changes the pulsation, and then this is detected by standard ellipsometry methods, by putting a quarter lambda plate and the Wollaston prism, which separates the two pulsations, horizontal and vertical, and sends into the balanced near-infrared detector. So if there is no near-infrared field, then your detector is balanced and you have the difference signal is 0. So the beauty of this method is that it detects not only the amplitude, but also it detects the amplitude with a sign. So basically, you reproduce not intensity as we usually got used to, but the field. And so once you get the field, and of course, this is a function of delay between these two pulses. And because we have a dual comb system, one comb is produced for the near-infrared, the delay is changed automatically. And so that's why you can see it on the oscilloscope. Basically, you reproduce the real field of the mid-infrared wave. And this is a beautiful technique. And we immediately started using that as soon as we mastered. It took a few months just to master this technique. We built another dual comb setup where we just instead of using a detector, we simply use the first frequency comb to double its frequency and to convert it to 1.2 microns and to use it as a probe pulse or gate pulse. And another comb at 2.4 was used to produce long wave pulse or mid-infrared or terahertz using, again, these two crystals. Then you use the gas cell, which you want to investigate with molecules at a very low pressure. And then here, the two beams are coherently combined. So that's why there is a 90-degree parabola with a hole. So the near-infrared pulses, because it has very small divergence, it just goes to the hole, and they are combined in this nonlinear crystal. And then you just use a standard ellipsometry method and send it to the in-gas balance detector. So the beauty here is to use an inexpensive room temperature detector in gas, designed for the near-infrared with a very low noise. And then you can detect anything which, in terms of the wavelength, you can go all the way to 300 microns and beyond. The only limitation is that you cannot go to shorter waves, because we should remember that our probe pulse should be shorter than the period of the long wave pulse. So in our case, the limit is, roughly speaking, 6 microns, but we are now working on how to compress, because now our probe pulse is maybe 25 per second. So we're looking forward to compressing the pulses just to be able to see all the mid-infrared range. So, and then you just get the signal from your pulse, and then you take Fourier transform, and you reproduce basically. So this is the spectrum without molecules present. So you reproduce your long wave comb which you see is more than an octave. And so this is terahertz is the wave number. So this is about 10 microns, and this is about 20 microns. By the way, you immediately see there, this is a two-phonon absorption in the gallium selenide crystal, actually. You can see that. So I should stress that this technique is also beautiful by another reason, that it senses the field, not intensity. So you can send, the dynamic range is enormous, because imagine that you attenuate your beam by 1,000 times, your field is attenuated by only 30 times. And so that's why in intensity we can get a very high dynamic range. And in Garching, they also do electro-optic sampling, but not with a dual comb. They say that it can get dynamic range of 16 orders of magnitude using electro-optic sampling. That's wonderful. And so we, as a demo, we just took these two molecules and measured the long wave spectrum of a mixture of CO2 and acetylene. And again, we compared them with a Hytron database, excellent agreement, even on this scale. So now, here I should say one important thing, is that the frequency comb basically is a discrete ultra-narrow spectral lines, but they are spaced by 80 megahertz. And you may think this is the repetition rate of the lasers. And you may think that you cannot do better than 80 megahertz. In fact, the answer is no, because you can always repeat the experiment and move the combs. Yeah, because each comb tooth has a delta function. It will see only where its frequency is. You can move the combs, and we already did that. And so now you can see that you can reproduce the Doppler line width, which is only 66 megahertz wide. So you need many more points, much more points than 80 megahertz. So in this case, we repeated the experiment 12 times by just moving the comb. So basically, the resolution is unlimited. It just costs you more time to repeat the experiment. And then we explored the molecules like methanol, which still has the data in the database. And then we went to very important exobiology molecules like isoprene and dimethyl sulfide. There are no databases for this molecule, and we generated exceptionally precise high-resolution molecules, spectra of these molecules, and there's nothing to compare. So now our theory partners working hard on this. They are almost deciphered, actually, and they also work on better deciphering on methanol. So we can really produce very nice spectra. And of course, the spectrum can be taken in 10 seconds, but if you care about signal to noise, better signal to noise, and looking for some smaller features, like these ones, you see, these are expanded features. We can average up to 8 hours, for instance. That depends, because the signal to noise grows as a square root. It grows slowly as a square root of time, but still you can do that. Terahertz region is also very interesting and very important. These are rotational bands of molecules, pure rotational bands. Here we took ammonia molecule. Why? Because ammonia molecule has dipole momentum, so it has absorption at terahertz and emit-IR simultaneously. These are wave numbers. So we have shown that in just a single interferogram, which is taken by electro-optic sampling, you see, we measure terahertz, but we don't need terahertz detectors because we use electro-optic sampling. From a single interferogram, we can, and this is, by the way, the spectral contour of our spectrum. In a single interferogram, we have shown that we detected the rotational bands of ammonia. Here they are. This is water. Water is everywhere. It's no, but with high resolution, it's no problem because you can also. So this is Hytron database, and you can see that you get a perfect correlation with hydron, and the same with the mid-IR. You see these lines of ammonia. So now we collaborate with spectroscopists because there's so many things to explore, so many things which are still unknown in this range. So now just a little bit of fun. So essentially, all the information which we obtain with dual Comb spectroscopy, of course, we get an interferogram where the two pulses get together, roughly speaking, 100 times per second. But of course, all the information is contained in the tails. On this scale, it will go for several miles that way. And in fact, if you zoom in into the tail of this signal, then you'll see the black one. This is not noise, because if I create the cell with molecules, you will see the yellow line. So these are clearly created by the free induction decay. So basically, yeah. Basically, the molecules they're excited and then they sink. And so just I want to show you how they sink. So we converted them into sound by slowing down by 25 billion times. Okay. Let's see. No. Somehow the sound does not. So this is what they do. They vibrate and they rotate. And these molecules play bass. Anyway, it's fine. Some musicians are very interested in that, so they're okay. So, and the application is obvious of this technique is one of the applications which you started doing is medical breath analysis, because that's the power of the frequency comb. You can simultaneously measure many. We have in our exhale breath we have about 1,000 biomarkers, and hopefully this will be good for early diagnostics of different diseases. And UV region. So it is kind of because my talk says to petahertz. Petahertz is UV. So how we got the UV region? In this case, we use the same pair of frequency combs at 2.4 microns, but we instead of down converting, we up convert them. So we take advantage of the two laser sources which are perfectly coherent to each other. And so we used nonlinear crystals to produce high harmonics. This is not high harmonics in the sense that people using high field physics argon. This is just, we use nonlinear crystal of lithium niobate, and we produce these high harmonics, and it's 8 harmonics 6 and 7 are in the UV range. And so, and then when in the UV, everything is much more sensitive to the vibration, because basically this dual comb is based on interference effect. And so you are more sensitive to any vibrations, mechanical vibrations, but still we were able to get interferograms, these nice interferograms for the 6 and 7 harmonic, and then we took Fourier transform, we saw the spectrum, and to our amusement, we see that this spectrum of the 6 harmonic contains 1 million comb lines, which is absolutely amazing. And the 7th harmonic is like slightly more than 500,000. And these are resolved comb modes. And so we decided to, so basically this spectrum, and this is the mode structure of the spectrum. In fact, it consists of delta functions. And then we did not find a good molecule to have a narrow enough spectrum to show our resolution, because in the UV, the molecules are Doppler broadened, and Doppler broadening is bigger in the UV. So we just decided, we took a volume, so-called volume Bragg grating. It's an ultra narrow band filter, reflection filter, which is based on writing a volume grating in the photosensitive glass. which we got from the company called OptiGrade. And then we look at the reflection spectrum, and really we got this very narrow spectrum. On the background is the full spectrum, and this is the zoom spectrum. And this spectrum was taken only in 1 second. And this is the interferogram corresponding to this 1 second spectrum. And these are nicely resolved modes with a finesse of about 3,000. So this is my last slide. And I should say that, let's say a year ago, we know nothing about UV. And so now we are very much interested in going to the UV because there was an interesting discovery, and I found that there will be some talks about that, on the nuclear transitions, which can be used as atomic clock, as a clock instead of using the atoms which are suspended in space. So it's amazing that the thorium isotope 229, we got used to the fact that atomic nuclear transitions are usually in X-ray and gamma ray range. And the researchers found actually that there is a transition which is in the UV at 148 nanometers. And so far, the best measurement with that was with the resolution of 10 gigahertz, which actually corresponds to this number, which is shown here for the lambda. In fact, we can measure it with 10 megahertz resolution or even better using moving the combs. So, and we are very excited about that, and we can, but we need to go to shorter waves, about twice what we have now. And of course, there are alternative ways of producing high harmonics. We don't have much power. We have only 14 nanojoules per pulse, as opposed to people who do high harmonic in gases. But there is a very interesting research in the generation of high harmonics in solids, like the ones shown here. So we hope that we can go to shorter waves because we have a very nice phase-locked laser system. And this is my conclusion. So we use a new platform, and based on the same platform, we can do measurement in the terahertz and the mid-IR and in the UV, and of course in the visible, that's trivial, with a resolution of 80 megahertz, which is very good for spectroscopy, but much less than that. The absolute frequency axis is referenced to rubidium clock, or GPS. We can do massive spectral data collection of, let's say, 1/5 or 1/4 of a million common lines at up to a video rate. And simultaneously, we demonstrated simultaneously measurement of mid-IR terahertz bands, which is important for spectroscopies because some of them work only in the microwave, some work in the mid-IR. And here you can measure the same molecule, the same experiment, and you can cross-link the strength of absorption, etc. And finally, in the UV, we produced combs with up to 1 million comb lines. And here, I would like to stop. I would say that we are open for collaboration, and we are looking for good PhD students and postdocs. Thank you very much.
Thank you, Dr. Vodopyanov, for the very interesting talk. Before today, I only had heard gravitational waves. Now I've heard how molecules sound too.
All right.
Fantastic talk, and it's great to see you also all this new technology coming into reality. So my question is, well, so you showed the comparison to heat-around spectra, and while positions of those lines, okay, also will are perfectly. I noticed that the amplitudes are not always matching the amplitudes from those tables. And this is actually related to the second half of the question is, ultimately you want to do the mixture of gases, and you mentioned breath analysis, and you are not talking about a mixture of 4, 7, okay, so you're talking about thousands of those. So can you give us a little bit more also of your vision, how you will deal with all these problems?
I understand only maybe the quality of the microphone was not very good, but so you say that you said something about the amplitude.
Yes. So if I look closely at your comparison with heat-run spectra, okay, so I see that actually the amplitudes not always match. Okay, also.
No. So of course, Heitran is always evolving. And so, that, of course, they use lots of our data. Yeah, and I should say that we are very pretty precise in the apps in this line strength. Yeah.
Hi. So a question about the dual comb electro-optic sampling measurements for the detection of the electric field profile coherently. I was wondering if it's possible also to measure the fluctuations of the field. That would be very important for infrared quantum optics, which is not fully developed.
Yeah, that's a very good question. So in fact, I collaborate with Alfred Leiterstofer and University of Constance. We built the subharmonic OPO, and we're doing a little bit of quantum optics based on just measuring the vacuum. You can measure the vacuum using electro-optic sampling.
Thanks, Konstantin. This was a great talk. I have a question on whether you see, especially in this spectral range where you're perhaps lacking photons, maybe towards the ultraviolet or the deep IR, whether you see an opportunity for squeezing these combs to do better sensitivity measurements, including signal-to-noise ratio. And following up on that, whether do you see like synchronously pumped OPOs as a way to produce this multi-mode squeezing, right? Or rather looking into Chi3, like optical squeezing, optical soliton squeezing type of approach?
And squeezing the combs, this is my question to you guys, because you know much more about quantum optics than I do. So if there are any suggestions about squeezing the comb, because I think that my intuition tells me that the subharmonic OPO is already kind of a squeezed comb, right? So maybe we can talk about that, because my knowledge is limited.
More questions?
Of course, yeah, extraordinary technology, extraordinary science, wonderful all around. Now the question is breath analysis. You briefly mentioned this problem of breath analysis, and usually, as you were thinking about this problem, having a source is only a part of the problem. Then you need to build a cell. Usually, it's a multi-pass cell, and then people of course freeze out water vibrations, and then this multi-pass cell. People have been using cavity ring down spectroscopy for a long time, and this is the other way to do this frequency comb in a way. So, are you doing?
Okay, let me quickly comment to your question. So, first of all, water is not a problem, because if you work at low pressure, reduced pressure, the lines become very skinny, and so water is not a problem at all. So the second part, we prefer multi-pass cell because of this reason, that your path length is defined, is fixed, right? In our case, 76 meters in a cell like that. So that's why if you want to produce the line strength for Heitran, you know exactly, if you know your pressure, your length. The resonantly enhanced cavity is a nice thing, because the effective length can be kilometer or 10 kilometers. However, you don't know exactly what is your path length, because today, you know, the resonant cavity works better than yesterday, and so you don't know, right? So that's why and of course it's not uniform in the spectrum. So from this point of view, and in addition to that, the resonant cavity usually has limited spectral range, typically 100 wavelengths. And we can measure 1,000 or 2,000 wavelengths. So, which is important for the medical breath analysis, because you're looking for many biomarkers. And now I got some grant from Air Force, so I'm studying this study with the breath analysis. Many people try to do that, but unsuccessfully, because usually they're very limited in spectral span, like QCL, quantum cascade laser. can be tuned over 50 or 60 wave numbers only.
So let's thank our speaker again.
Yeah.
Our next speaker is Ron Foreman. Ron, I'll let you know when you have 5 minutes left. Okay? Thank you.
Hello, everybody. I received notice that I should give this plenary talk an hour ago. So I guess you'll agree with me that that's the definition of short notice. No, so what I did actually is I'm giving next week a mini course in Oxford as the summer school for ICAP. So I quickly took slides from that mini course, and so maybe actually this means that also the students here will be able to enjoy some slides, and also I hope the researchers will find things that are enjoyable to them. Okay, so can a rock be a wave? From 100 years of de Broglie wave packet duality to quantum gravity. It's 100 years of spectrum to cover, and we'll try to do it. Well, first of all, you know these two gentlemen. The first one is de Broglie, and the second one is Otto Stern. We are now celebrating 100 years to de Broglie's thesis and 100 years to the Stern-Gerlach experiment. Different places around the world are celebrating now different anniversaries. I was just in Glasgow, and they're celebrating, of course, 200 years to Lord Kelvin. But today I want to celebrate the anniversary to these two people. I noticed that both of them have mustaches, so I looked for a cartoon of a scientist with a mustache, and this is what I found. And the rock we are talking about today, just to put everything already in perspective, the rock I will be talking about today is a nanodiamond. Yeah, so that is something like 10 to the power of 11 carbon atoms, and that is something like 10 to the minus 15 kilograms. So it's already a rock. Yeah, that's what we'll be talking about today. Okay, before I start, our group does quite a bit of quantum technology, so I just want to flash at you. I will not talk today about quantum technology, but just want to flash at you some of the things we're doing, which I find fascinating, especially the interface, how information goes from fundamental science in our lab to quantum technology in our lab. So very quickly, we're doing miniature cold atomic clocks. You see here a pyramid moth with a moth here. This is how it looks like. It's already with the industry. The prototype is already with the industry. All optical magnetic sensors, that means fiber going in, fiber going out. There is a vapor cell here. Either cesium for a simple magnetic sensor, or potassium, rubidium, and helium for what's called a co-magnetometer, which we use to detect axion-like dark matter in our lab. Optical frequency standard, we have optical lattice clock with the terbium in our lab. We're actually part of a European consortium that wants to redefine the second, moving from microwave clocks to optical frequency standards. And perhaps the last thing I will mention here is spins in diamond, which we will talk about today, the diamond. So here you see an example of using it as a sensor. So what you see here is actually flux, magnetic flux from vortices in a YIPCO superconductor. They're imaged by a thin layer of NV centers that we put onto the superconductor. And people from the high TC superconductor field, they hope that this will give them new input on how to reach higher temperatures. These are two papers we put in the archive just a few days ago on technology, metrology with interferometers. This I will speak about today in session 7, the last talk of session 7. Squeezed point source interferometry for rotation sensing. And this was done with NIST. It's geometric phase amplification in clock interferometer. It's a long title, but this for me is a very nice example of how fundamental science moves to quantum technology, because first we had to learn how to do clock interferometry some 10 years ago. Then we had to learn how to measure geometric phase, the Berry phase, and the less known Pancharatnam phase. And then we could do this together with NIST. As I said, it was just put on the archive a few days ago. And of course, our former students, were very proud of them and how they work in the high-tech industry. And maybe I give here one example of a former PhD student, Tal David, who just recently received $25 million as a seed fund to open up a quantum computing company. So we're very proud of our students and helping them with their new career in the high tech. Okay, so the outline of the talk will be motivation. Why am I interested in de Broglie and Stern-Gerlach and in rocks? Rock interferometry, and I'll go through a very quick reminder of complementarity, atom chip, and Stern-Gerlach. Then I'll start going into witch path information, which is actually decoherence or distinguishability in Stern-Gerlach interferometry. I'll talk about the sequence of the experiment we're planning, some preliminary results, and some special decoherence channels that exist only with rocks, not with atom interferometry. And time permitting, I'm not sure we will have, I'll go back to de Broglie and talk about something that people less know about him, or it's less popular about de Broglie, and that is his pilot wave, which turned later into Bohmian mechanics in the 50s and 60s. And I want to show you something new that we wrote last year, we published last year about this topic. We already published quite a few feasibility studies, and you can find them on our website. So I already showed that this is the rock we're talking about. It has a single spin in the center. So I mentioned carbon atoms, but this rock has a single spin in the center. It's an NV center. And so this single spin will allow us to do Stern-Gerlach splitting and interferometry, just like we do with the atom, with spin up-down. And so we're really moving from doing atom interferometry at the 10 to the minus 25 kilogram. We are trying to jump 10 orders of magnitude in mass in these interferometers. Okay, so what is the motivation? Well, in 2017 appeared this paper, and here I show the first two authors that since then work with us continuously on realizing this experiment. The idea here is to take two nanodiamonds. So you have here two nanodiamonds. Each one has a single spin. And each nanodiamond undergoes what we call a full loop interferometer. We are trying to do it with the Stern-Gerlach. There are other methods that I'll show as well. But so this is one interferometer, this is a second interferometer. Now this wave packet is going to be very close to this wave packet, let's say a few tenths of micrometer. There is a sweet spot where the gravitation, if they're heavy enough, and that's why we need heavy rocks, if they're heavy enough, the dominant interaction here will be gravitational. Stronger than spin-spin, than van der Waals, than Casimir-Polder, anything, they're neutral, of course, anything else that we know. Eventually, you see these two nanodiamonds coming up here, and you measure their spin. And you do a belt-type measurement on the spin, and you look for non-classical correlations, what we call entanglement. And the claim is, and you can argue that claim, but the claim of theoreticians is that if you see entanglement or non-classical correlations between these two spins, it had to be mediated by the gravitational interaction, and this is proof that the gravitational interaction is quantized because they claim that only a quantized field can mediate or initiate entanglement. Okay. Long before that, just with a single interferometer, we'll be able to test quantum mechanics in new regimes, theories like the continuous spontaneous localization, many orders of magnitude more than the state of the art today. The state of the art today, by the way, in heavy object is from Marcus Arndt in Vienna, 2,000 atoms in a molecule. We can test exotic theories like the fifth force, and we can test exotic gravity interfaces like the Diosy-Penrose collapse or self-interaction. There are many exotic ideas out there with gravity waiting to be tested, and this could be done already with one interferometer. But the big question is, can we split a large mass? It has never been done before, and we don't know if we have the technology to do it. Okay, so that is actually the topic of my talk. Can we split a large mass? So, to really understand the fundamentals of an interferometer, we go back to de Broglie and to his wave-particle duality. And again, it's 100 years to his thesis. And he's well known for the wave-particle duality, called also complementarity, had all kinds of equations written. For example, wave-like and particle-like equal 1. If this goes up, this goes down. Or visibility of interferometer, if it goes up, distinguishability goes down, or vice versa. And we will talk about this distinguishability, which is actually decoherence, or collapse, if you like. And sometimes this is also called Witch-path information. And de Broglie, of course, was known for many other things as well. He claimed that quantum mechanics is incomplete. Pilot wave, maybe we'll get to it at the end. Bulk frequency, also known as Compton frequency. I will not talk about all these topics today. Okay, you might say complementarity is trivial. I want to show you that it is not so. And I want to give you 3 examples for complementarity experiments that are not trivial. In fact, we're not sure what should really be the result. So the first one is the following. Let's take the double slit experiment. You know it very well, but you have only one slit. So you say, okay, from one slit, how can I do the double slit experiment? I put the slit in a coherent quantum superposition of 2 slits, 2 locations. But you have just one slit. It's in a superposition. Now some probe particle goes into your 2-slit system, or 1 slit in a superposition system. So, will you get interference? That is a question that has been asked by several theoreticians before, including Claude Cohen-Tanuji. There's still unknowns about the answer. I won't have time to go into it, but we also went into this discussion, and you can find this again on our website. This is the answer to this question of whether you will see interference or not. And the answer is, it depends. Okay. All right. So another example I want to give you on the complexity of complementarity is time. Can time be Witch-path information? Yes? Okay. So can time create a collapse or a distinguishability? So this is an idea that actually came from the Bruckner group in Vienna. We saw this paper and we were very excited about it. He says, take an atom, put it in a state of a clock, and send it through a Mach-Zehnder interferometer. So it's one atom, one clock, and you have 2 wave packets of the same clock, and put it in a vertical direction above Earth. So there is different proper time from redshift. So the different wave packets, the 2 different wave packets, they see different time. What would that do? Is that distinguishability? And so we were very excited by this. He says that this is a quantum effect that cannot be explained without general relativistic notion of proper time. And we went on to do this, a proof of principle, because our clocks were not sensitive enough to the real redshift of Earth. So we had to form a synthetic redshift of Earth. But anyway, it was a proof of principle experiment, and now several groups are trying to realize it with the real redshift of Earth. Anyway, we found that yes, just like he predicted, just like the Bruckner group predicted, this is interferometric visibility, and this is the proper time difference between the two wave packets, and you get oscillations of visibility. You get oscillations of visibility because sometimes the clock shows the same time up to 2 pi on the Bloch sphere, and then you get visibility, but the two wave packets can show different time, visibility is lost. Okay? So this is really a complementarity with time. And the third example I'll show you, and the third and last example I'll show you, is let's say we take a rock like a nanodiamond. It already has phonons, so this blue and red are just a picture of orthogonal phonons in this rock. And we now are close to having the technology of sending this rock through a single slit. You know that in double slit experiments in the old days, they always put a single slit. It was called a coherent slit, just to increase the transverse coherence length of your wave, so it covers both slits. But anyway, we all know how to calculate this sinc function that we get. We all know how to do it. We teach it in our undergraduate courses. But there is no quantum theory that we know of that tells us what will happen with the phonons if in this slit. Because if a particle gets momentum up or momentum down, it depends what slit it gets, will there be orthogonal phonons coming out of the correlated or entangled with these two different momentums? And as far as we know, and I've talked to quite a few theoreticians about it, there is no known theory to give an answer. Okay, so complementarity is still very much a hot game. And so now I will talk about center of mass. Today I'll talk about the center of mass of these nanodiamonds. And in our lab, it's very easy to see that De Broglie was right when he said that a particle is a wave. This is a double slit interference experiment we get with cold rubidium atoms in our lab. It's very easy. And the question is, can we do the same thing with a rock? So I repeat the questions just so you understand what is the challenge that is facing us. Okay, so people know how to split an atom, coherently split an atom, now for decades. One of the most popular ways to do it is to do Raman or Bragg transitions on the atom, to do pi half, pi half, and you get a beautiful interferometer. Yeah? And people have already done high-tech industry with it. This is from UQANs. This is from Sandia, very, very small. Now people are going actually into a chip. This is a 500 micrometer wafer, silicon wafer, and the vacuum chamber is actually inside. You'll hold it, and it will look like a normal Pentium chip, but it's actually inside. There will be a vacuum chamber with an interferometer. So this is all really beautiful, but probably not very useful for rocks. For many reasons. One of them, you need a lot of momentum transfer to actually get a splitting. It's very heavy. The rock, you need a huge force, and it's opaque, and you don't have very well-defined transitions. There are many reasons why this would not work for rocks, but still, optical potentials might work. So, for example, this nice paper that just came out this year is trying to use Hill potentials to stretch and split the wave packet of the macroscopic object. And there are other ideas. This comes from Marcus Arndt's group, using all kinds of lattices to do interferometry. So there are quite a few ideas out there. But we would like to take a different route, which was taught to us by Stern and Gerlach. Here you see them. By the way, between them you see Lisa Meitner, not so well known, was working in Berlin until she had to escape in 1938, and she was nominated 48 times to the Nobel, never received it. Several historians are still trying to figure out why. The building of Stern Gerlach still stands. It's a European Physical Society historic site. You can visit. And in 2019, we inaugurated it. It's a very beautiful place to visit. Okay, so just in last December, Quanta magazine came out with this article, very nice article reviewing the history of Stern Gerlach. I recommend to read it. And they also talked about our attempt to go and do a gravity experiment with this technique. I want to very briefly, that was my reminder of what is Stern-Gerlach and what is complementarity, and now I want to briefly remind you of what is the atom chip is and why we have to use an atom chip in this experiment. So atom chips were started more than 20 years ago, maybe 25 years ago, and they were used for ground state atoms. Now they're used for Rydberg atoms, molecules, even NV centers, ions, cold electrons, and even at CERN, they're thinking about putting anti-hydrogen on atom chips to localize them very well and trap them, and maybe do interferometry with them. Anyway, so atom chips are really still going strong, and this I already explained to you what this picture is, and we are actually serving the community. In our university, we built a fabrication facility that is dedicated to atom chip, and we send these atom chips or ion chips. This was a chip sent to Mainz, for example, in Germany, this to Amsterdam. The two most recent chips that we sent this year were to Paris, to Gabriel Hetet for the nanodiamond experiment he does, and to Trento for levitating macroscopic permanent magnets. Okay, so if you have an atom chip that you need, you're welcome to approach us, and there are, of course, many review papers that are available. This is an artist's view of how an atom chip looks like, all kinds of current-carrying wires and electrodes. Today, it's a jungle of technologies with light, near-field light, far-field light, microwave, RF, electrodes for electric fields, magnetic fields, whatever you want is there. Here are the atoms. Here's how it looks like in the lab. You see a BC and its reflection from the surface. It's very close because the BC is only a few microns from the surface, and you see the electrodes. And 3 atom chips already made it to space. International Space Station, beautiful atom chip from Cold Quanta in Boulder, Colorado, and they're doing very nice interferometry experiments. And this is the first atom chip that made it to space with the German Space Agency. And now one of my former postdocs is putting an atom chip on the Chinese space station. All right, so why do we need the atom chip for this experiment? Well, the first thing that the atom chips can deliver is very high magnetic gradients. When you think magnetic gradients, when you think Stern-Gerlach, you need magnetic gradients. That's the force. You all know that. But what can give us strong magnetic gradients? The first thing you think of is a coil. But apparently coils are not good enough. And the main reason is that typically a large coil is quite far from your particle. And that's why the magnetic gradient falls. What we can do with the atom chip, we can do extremely thin wires on the atom chip, and we can bring the particle to a distance of a micron or a few microns from that wire. We can push high current density, and although we push only 10 amp, for example, at a distance of 1 micron, you get 10 to the 6 Tesla per meter. No coil on Earth can deliver that. Okay? So that's the first reason. The second reason is because it's straight wires and not coils, we don't have inductance, so we can turn on and off in microsecond, maybe even nanosecond. That's very important, and very high position accuracy. Okay, so the next question is, why do you want to go to Stern-Gerlach? Has anyone even proven that is a coherent splitting? And many theoreticians actually claimed for the last 100 years that it is not. Stern-Gerlach did not observe any interference pattern. They just observed the 2 points that you see there, or the 2 lines that you see there. This could have been done also by a statistical mixture. If half of the beam would be spin down and half of the beam would be spin up, they would get the same result. There was no proof in the Stern-Gerlach experiment that this was coherent splitting, and this is opposite, or in contrast, to what textbooks teach our young students, undergraduate students. Okay, so the question is what is written in textbooks true? Well, we don't know. And so you have to do interference to do that. So we started 10 years ago to do all kinds of interference experiments with rubidium atoms, Stern-Gerlach rubidium atoms. We started back in 2013. We observed this interference pattern. And then I told you about clock interferometry, geometric phases, and then this full loop, which I will tell you about in a minute. And what we know is that, yes, you can get coherent splitting from Stern-Gerlach, at least for atoms, cold atoms. We don't know about nanodiamonds. That's the big theoretical question now. And let me tell you about the first experiments we did already 10 years ago. So this is time, and this is a spatial coordinate. So you take an atom with some spin, you put spin up plus spin down with the pi half pulse, you put in a magnetic gradient from the atom chip, then you again mix the spins not to have orthogonality. Eventually it's a double slit experiment with two wave packets that having the same spin, and then you let them expand and you get this nice interference pattern. We did it both with the BEC and with the thermal cloud. Okay, so that works well, but it's not good enough for the nanodiamond. It's not good enough for the nanodiamond because if we need here a long time to let them expand, and the nanodiamond doesn't have a long time. And the reason why it doesn't have a long time is because the decoherence rate is enormous. So with the nanodiamond, we have to do something much more quick. And much more quick is this. This is called the full loop Stern-Gerlach interferometer. People have been dreaming about it for a century now. This picture is from a book by Bohm from 1951. They didn't have the atom chip then in mind. They thought about magnetic gradients. You see here 4 magnetic gradients for splitting, stopping, accelerating back, and stopping again. So there's no expansion time needed because you force the two wave packets by force. You force them to come back together again. The signal is no longer a special interference signal. It's now a spin oscillation signal. Okay, but now I go back to de Broglie and distinguishability. What is going to be the distinguishability here in this kind of experiment? Well, the first thing is time irreversibility. The first problem is time irreversibility. Why is that a problem here? Because if you want the two wave packets to really get to be on top of each other, that's what you need. Full overlap, both in momentum and position. You need to do a full time reversal operation. The second half of the interferometer has to be full time reversal of the first half of the interferometer. And that's a problem. You all know about time irreversibility. This was quantified, actually, it was discussed by many people in the context of the Stern-Gerlach interferometer, Heisenberg, Wigner, Lamb, Bohm, Fermi, many people. But it was quantified for the first time by these three gentlemen here, who called it the Humpty Dumpty effect. And they quantified it as an exponential drop in coherence or in the visibility of the interferometer, depending on what? On delta Z, Z, and delta P, which are here the experimental imprecision of how good we closed the two paths. How good is the overlap in momentum and position? What is the scale of how good we have to be? It's this initial spread in momentum and position of the wave packet. For example, how good we cool the wave packet. So this is very, very hard, this exponential drop. So you know you have to really control the full thing, and time irreversibility is a big problem here. Okay, that's our first problem. So now we are really going to do the experiment, and we have now, instead of 2 magnetic gradients, 4 magnetic gradients. How much time do I have? Okay. Okay, thank you. So now, instead of 2 in the double slit-like experiment, we have now, in the full loop experiment, 4 magnetic gradients, again, to split, stop, accelerate back, and stop again for full overlap. And then we measure here oscillations of the spin population. Now, this is what we want to do with the nanodiamond. Now, a small anecdote, but an important anecdote. When we first thought of doing this experiment with rubidium atoms, this gentleman here, Wolfgang Schleich, who will give the plenary talk tomorrow morning, came to us and said, well, you're probably not aware of a prediction made also almost 100 years ago by Kennard. And this prediction said that if you manage to do such a full loop experiment, you're going to have a very unique phase accumulation rule, which is going like t to the power of 3. If you look at normal interferometers today, matter wave interferometers like the Ramsey-Bordet or the Kasevich-Chu, they work like t to the power of 1 or t to the power of 2, or t is the interferometric time. But this interferometer is going to have a very unique signal. So we indeed asked him to do the theory for it, which he did. Some of the people here are from his group. And they did the theory, we put it there, and we put the data on it, and it fits perfectly. So really, this interferometer is going to have a unique signal, and for us it's very, very nice, because it means that if we see that signal from the nanodiamond, it's really a verification that we have verified coherent spatial splitting, because that's the only way to get this t to the power of 3. By the way, some people think it's a very fundamental rule, this t to the power of 3. This paper came out of Oxford, that it's sort of a quantum equivalence principle. And Penrose likes to tell the story, and this is a paper that he wrote with Yvette and Richard, where you see that he claims it's actually the difference between a wave packet, a quantum wave packet in the Newtonian and a quantum wave packet in the Einsteinian frames of reference. The difference here is in the phase of t to the power of 3. So it could be also very fundamental, but for us right now, it's a very unique signal. So 3 years after we first came out with splitting, coherent splitting of Stern-Gerlach, came out this paper, which actually suggests to use the full loop Stern-Gerlach on a macroscopic object. You see here the spin up plus down. You see the magnetic, this is time now, and this is spatial dimension. You see the splitting in the gradient, the recombination in the gradient, and then the measurement of the spin. Okay, this you already saw. This paper came a few years later, and there are many models. I won't have time to go through them that are waiting to be tested. I already mentioned the Diossi-Penrose collapse model. They claim actually that if you have a heavy object in a superposition, it creates a superposition of curvature of space-time. And the claim is that a superposition of a curvature of space-time is unstable. Thank you. And therefore, there will be a very fast collapse, much faster than what we expect. This is another thing we want to measure. Some people even claim that there's going to be self-interaction between the two wave packets, so much so that there will be the Newtonian trajectories of the center of mass will come closer. That we'll see immediately. Yeah? They say that gravity is unique in that sense because this has not been observed in any other interaction. Okay, so what do we need to do? We need to have a source of single spin nanodiamonds. That's already hard. We trap them in a Paul trap. They're charged. To cool them, we need to do cooling down to the ground state. We need to neutralize them. Otherwise, the interferometer will have very high decoherence because of charge. Then do the Stern-Gerlach interferometer that you already saw. Recapture them and do it all over again for data. This is the chip we are now building. So it has 2 layers and a gap of 2 millimeters in the middle where the interferometer is going to happen here in the middle. And you see here simulations of the trajectories of the 2 wave packets of the nanodiamond. And of course, we have to learn a lot about NV centers in nanodiamonds or in diamonds. And this is all the work that we did so far with NV centers in diamond. And our chip is already, a first version is already being tested in mines in the group of Ferdinand Schmidt-Kaller. You see here the double chip with a gap, 2 millimeter gap in the middle. This is the wire that's going, and he already trapped ions in it. This is the high current density wire that is going to give the Stern-Gerlach pulse magnetic gradient. You need to develop new materials that can withstand very high current density. And these are the source of the nanodiamonds. You see these pillars here. This is the source of the nanodiamonds that have to be very accurate in size and shape. Some preliminary results from the lab. You see here a nanodiamond trapped in a Paul trap, but this is a very rudimentary Paul trap, not a chip. And some ODMR spectroscopy already of the NV center in the center of it. By the way, the whole field of levitating microscopic objects is now called levitodynamics. It's a very hot field, and there are quite a few review papers that you can already read about it, and some people claim in terms of metrology that it will be much better than normal atom interferometry in terms of sensing, acceleration, gravity, and so on. I will finish with 2, we talked about distinguishability of de Broglie. I will finish with 2 unique decoherence channels that we had to look into that you don't have with atom matter wave interferometers. One is phonons. You don't only have an external decoherence from the external environment. Yeah, that's what we're used to. And that's, for example, coming from black body radiation. So it's the effect of an external environment. But here with the rock, you have an internal environment, an internal classical environment, which you can model as phonons. Yeah? So what Carsten Henkel, a theoretician from Potsdam, did, he first of all had to model the phonons inside this rock. And then as a function of object size and the splitting we want to achieve, he actually showed that this kind of distinguishability is much harder to fight than external decoherence, so external environmental decoherence. So this is a limit. If anybody is dreaming of putting a car in a superposition in the future or a rocket in a superposition in the future, you really have to look at the internal environment before you look at the external environment. Okay? And another problem with rocks is that even if you get a full overlap, here you see again the two trajectories of the two wave packets. This is real space, this is time. They fully overlap in momentum and position, as Humpty Dumpty asked. But if you look at the rotation angles, so you have these 2 degrees of freedom in rotation space, the two wave packets are far from recombination. So this is Humpty Dumpty, not in X and P, but this is Humpty Dumpty in theta and omega, Okay? Nothing to do with external decoherence or internal decoherence. Humpty Dumpty has nothing to do with external environment or internal environment, it has to do with experimental imprecision. All right, so this was published, you can read all about it, this was published last year. Okay, let me conclude. I think that De Broglie and Stern-Gerlach are far from completing their historical role. We're still learning a lot from them. I hope I convinced you of that. Fully understanding their ideas might enable us to create a verifiable spatial superposition of a massive object. This whole business, as I said, is called now levitodynamics. If we do succeed in this very hard experiment, it will be because of the groundbreaking works of many people that I don't have time to mention here, but really it's a huge field and people are making amazing theoretical and experimental contributions to this field, cooling to ground state, to the ground state and cooling rotation and so on and so forth. And if you're interested in our decade-long experiments on Stern-Gerlach, this was recently put in a book in honor of Otto Stern, this chapter. And so you're welcome to see it. In the last minute I have, I want to go back to an unpopular idea of De Broglie and tell you why I think it still has merit. And this is his pilot wave theory. And of course, he abandoned it. De Broglie abandoned it. There was a lot of opposition to it. He abandoned it. But then he came back to it when Bohm started to write his Bohmian mechanics paper in the 50s. Okay, now it's called the De Broglie-Bohm pilot wave theory. And the Bohmian mechanics, I have to stress, it gives exactly the same predictions as quantum mechanics. It's not a new theory. It gives exactly the same predictions. But for us, it's a new language. For the brain, it's a new language. So it allows us to think of experiments that otherwise I would, if I just had the language of standard quantum mechanics, I would not think about. So what I want to show to you very quickly is this paper that we published last year on how it allowed us to think of a new experiment. So we suffer with the atom chip with from van der Waals and Casimir-Polder. We bring the atom too close, it is attracted and stuck on the surface. This is well known. We thought, can we actually undo Casimir-Polder and van der Waals? How can you undo Casimir? It's a fundamental force. Well, then we remembered that Bohm always talked about the quantum potential, okay? It was never measured by anyone, and it's just maybe a figure of our imagination. But we took his equations for this quantum potential, which is actually, it comes from how you engineer the shape of the wave function. And we engineered the wave function such that the quantum potential, according to Bohm's equations, gives you the exact same Casimir-Polder potential, but with the opposite sign. So it cancels it. And what you see here actually is distance from the chip. You see here how the quantum potential in blue, you see here the wave function in black, the wave function, you see here the ripples. It's hard to see the ripples, but you see here the ripples. Yeah, so we had to engineer it in a specific way. And you see in blue what kind of quantum potential we got from Bohm. And actually it's normalized to the wave function, otherwise it would go high, very high up here out of the graph. But here you can see the residuals. The residuals are zero. There is no Casimir-Polder left. So this kind of experiment, we're planning to actually take the atom, put it very close to the surface, and try and engineer the wave function such so there's no pull of van der Waals or Casimir-Polder to the surface. So I just want to say that a different language for the brain is sometimes quite helpful. And I want to say goodbye to De Broglie by quoting what the famous John Bell said about him, and that is that Long may Louis de Broglie continue to inspire those who suspect that what is proved by impossibility proofs, and there are many impossibility proofs about quantum mechanics, of course, is lack of imagination. I think this is a beautiful quote from John Bell. I have to thank all the students that worked over the years on the Stern-Gerlach experiment and the many theoreticians that worked with us along the road, and the funding agencies, of course. I have to say that we're always searching for good students and postdocs, and I thank you for your attention.
Thank you for the very nice talk, Randy.
Hi, Ron. Great talk. So how big is your current rock, the rubidium BEC, in comparison to C60 that people have used in these kinds of devices, and grabcidin, which is a big molecule?
Our Stern-Gerlach experiments are single particle experiments. Although we have a BC, it's not part of the physics. I mean, it's a dilute BC, and it's just a source of many atoms for us, many cold atoms. So we never talk about the mass of the BC. It's just single particle experiment being repeated many times, the number of atoms you have in the BC. So we're nowhere near the state of the art in the, which is, as I said, coming from Vienna, from Marcus Arndt's group, which is a molecule with 2,000 atoms. Okay, that's the state of the art. We have never tried anything more than a single rubidium atom, right? And now, as I said, we're trying to jump 10 orders of magnitude. So that's a challenge.
Thank you.
Yeah, thanks, Ron, for the great talk. I was wondering when you say that we can wonder, one of the funny theory that you could test is that maybe there is a self-interference between the two parts. Self-interaction. But this could also be true if you just have a single electron going to two slits by just the Coulomb interaction. So did somebody observe that? Other theory about that?
You're completely right that we should have observed it with all the interference experiments we did, because if we have a Coulomb interaction between an electron, two electron wave packets going to a double slit, we should have observed it. But the claim of all these theoreticians is that gravity is unique. That's the claim. Now, many people are claiming that gravity is unique, but you know, I don't know if we'll see it. This is very easy to see, by the way. There was never a gravity experiment or never an interferometer with a very heavy object that we could see it. But anyway, that's the claim to answer your question. Yeah.
So in the experiment where I have where I have two interferometers separately, how close do I actually have to get my nanodiamonds to electrically neutral? And if I do get them to even perfectly electrically neutral, what about maybe some permanent, or not permanent, but electric dipole moment that I might have on my nanodiamonds just because there's some distribution of charges on the surface or something like that?
Yeah, so
overpower the gravitational interaction.
It's a great question. There is a huge effort here in terms of material engineering, first of all, to make sure that the charge is zero, that there are no patch potentials creating any dipoles, like surface dirt on the, it's a huge material engineering effort, yeah? Also to get the coherence length, the coherence time of the NV center to have at least the time of the interferometer. That's another effort I didn't even speak about. So definitely you have many forces that could be at work, and you have to make sure that they're not there. But Casimir-Polder, spin-spin, van der Waals will always be there. And Anupam and Sugato, both that I mentioned before, are working hard, and they already have several publications on calculating all of these forces. And as I said, there are sweet spots where gravitation is dominant by at least an order of magnitude, a few tens of microns. That's the distance.
So I was wondering if you can think of Ramsey experiments with delayed Raman pulses to see the interferences with nanodiamonds.
You're talking about Ramsey, if I understood you correctly.
Yeah, Ramsey with delayed Raman pulses.
Yes, so I'm not sure how that experiment really looks like, but in any case, the big issue here, Ramsey, for me, has no spatial splitting. So we do a lot of Ramsey, but it has no spatial splitting. We have to put in some kind of force. That is the big issue, that people are looking for what force will be able to spatially split a large object. So that is now the big question, spatial splitting. So all these things, exotic theories that I said we want to measure, we will have to have spatial coherent splitting in order to measure these exotic theories. So just doing Ramsey, it will not be good enough. Yeah. Yes, you're talking about time splitting, or yeah. But we really need, for these exotic theories, we really need spatial splitting. Yeah. By the way, also to test quantum mechanics in new regimes, we want to have, because the spatial splitting, the coherent superposition principle, it works in many dimensions, but I think the spatial dimension is perhaps the most dramatic one, and that's where we want to test quantum mechanics.
Yeah. So, here. Thank you for the very interesting talk. So I have a question about this irreversibility in time. So because you show that this depends on the extension of the wave packet, right, of the free particle. So this idea of fundamental decoherence.
The irreversibility has to do with experimental imprecision. Even if you have no environment, no decoherence from the environment, you're in deep space with no environment, the problem is that experimentally we're not perfect. So we have to, with the second half of the interferometer, the recombination part, we have to exactly undo the first part, which is the splitting part.
Okay, so there's no fundamental limit.
So what?
No fundamental limit.
Well, there's no fundamental limit, but at the end of the road, you have shot noise. You have shot noise everywhere in your currents. If you can give me squeezed currents, by the way, I'll be very happy, because then I go beyond the fundamental limit of shot noise. We have a lot of fundamental limits in technology that give us, that make us fear this kind of Humpty Dumpty effect very much. Yep.
Last question by Alexei.
Thank you for a beautiful talk. I have a naive question. So if I have two quartz oscillators and put them on two tracks and put one on a flat road and one through mountains, so it accumulates some phase due to gravity, and then I just combine them by cables to some combiner, I will have interference, much like one you showed for atoms. And if one accumulated phase phase, it will be 0 on the output. If one accumulated phase 2 phase, it will be 1 in the output. And they even will decay because these two oscillators have phase stability, finite phase stability. In this sense, experiments which you showed with interferometry may be interpreted as a classical interference. So where quantum comes in? Do you have some kind of tomography measurement, or like where you can say that it's actually quantum, but not just classical interference of two oscillators?
Well, I'll be very happy if you show me an interference pattern of two classical oscillators or two heavy oscillators. I don't know of such work. So I think that if we see an interference pattern of a single particle, and it's verified to be a single particle, I think we can call it quantum. I've never seen anything again, that resembles this kind of observable as an interference pattern with two classical oscillators. So if you have such work, I'll be very happy to see it. Yeah.
All right. Let's thank Rowan and all the speakers of this morning's session.
Thank you very much.
We'll come back at 2:30 with the parallel sessions.